Welcome to Edisoft Virtual Labs. The aim of the experiment is to determine the spring constant, the acceleration due to gravity, and the effective mass of the helical spring. The apparatus used will be a rigid stand with a clamp, a helical spring, a scale pan, a light pointer, a meter rule, masses, and a stopwatch. Several types of springs in common use can be classified by shape. The type in concern, the coiler helical spring, is a metal wire rod wound into a cylindrical shape. It can be designed either to compress under a force or to resist a force as it is stretched. A helical spring subject to extension by an applied load conforms to Hooke's law, which states that in the elastic region the stress is proportional to the strain. In other words, the load is proportional to the extension it produces. Mathematically, Hooke's law states that the applied force F equals a constant k multiplied by the displacement a, the change in length x. The negative sign indicates that the restoring force of the spring is always in opposite direction to the displacement. The value of k depends not only on the kind of elastic material under consideration but also on its dimensions and shape. If a graph is drawn after the initial loading, where some force is required to separate the turns of the spring which are pressed against each other, a straight line is obtained of extension against load. From this portion, the extension per unit mass n of a load can be obtained from the slope, where the slope equals g divided by n, and from which k equals g divided by n. If now a mass m is attached to the spring, and the spring extended a further distance x, a restoring force of x by n multiplied by g is called into play. The spring, on being released, executes vertical oscillations. The equation of motion of mass will be in the following form, where g divided by m and represents the oscillating frequency. The motion is thus a simple harmonic, and the periodic time will be in the following form. The above analysis assumes the spring to be weightless. If not, the load m must be increased by a constant amount equals to the effective mass of the spring. Then the equation will be in the following form. If a graph of t squared against m is drawn, a straight line is obtained from which the acceleration due to gravity and the effective mass of the spring can be found as mentioned before, where g equals 4 pi squared n divided by the slope, and the intercept on the axis of m gives the effective mass of the spring. Now let's start the experiment. Part 1. Determination of the extension per unit mass. Let the position of the mark to be the 0-point y node. Put a load in the scale pan and note the new mark position and deduce the extension delta y. Repeat the previous step with different loads and note the extension delta y for each load and tabulate these results. Plot the relation between the load and the extension delta y and calculate n. Part 2. Determination of the acceleration due to gravity and the effective mass of the spring. A load is added to the pan, which is set in vertical vibrations by giving it a small additional displacement. The periodic time is obtained by timing 20 vibrations, 3 times at least. This is repeated with different loads and a graph of t squared against load is plotted. from which the acceleration due to gravity and the effective mass of the spring are found as mentioned before.